All right, so first of all, my name is Stephen Donnelly. I'm CTO at a company called Indes from New Zealand, and we are a sponsor of Wireshark. And what we do is we build packet capture hardware and appliances. I'll try not to talk too much about the company. So this talk is a little bit meta. So for a lot of the talks today, we've been looking at TCP analysis and a lot of depth. Really getting down into individual packets and that kind of thing. What I want to do in this talk is take a little bit of a step back and think about the context about how do we capture packets and why do we do that. So if we're here, I think we're people who are interested in packets. We're either capturing packets today or we're analyzing packets, we're trying to work out problems with networks, or we want to be doing that and we're learning how to do it. Why do we capture packets? So, you think about it, the reason that we capture packets is because it answers the questions, right? Packets are the ground truth. If you have a problem in your network, or you think you have a problem in your network or with your application and you want to understand what's happening, we often say packets are the ground truth or PCAP or it didn't happen. So if I'm the networking team and I'm trying to say that the network is working okay, I need a PCAP file in order to do that. Likewise, if I'm the application team and I'm convinced that the network isn't working right, I can't convince those network guys until I can show them a PCAP file that proves that it must be the network that's wrong. So very frequently, a PCAP is all you need. You take a PCAP packet trace recording that you've done on your client or on your server, and you can then point a finger very accurately at somebody and say, must have been the IDS vendor, must have been the network, or whatever. And we started to think about this a little bit, and I kind of wondered, is that always true? Is it always true that all you need is a PCAP file, and then you have the correct answer? And this is a great saying. You can get it on a t-shirt. These net reset guys have got it. I was talking to a customer one day, and what he said was, PCAP or it didn't happen, or another way of saying that is, packets never lie. Right, so if you have a packet trace, that was what was really on the network, you have ground truth. But what he said was, well, packets never lie unless you don't know where they came from. So there's a few cases where a PCAP file by itself might not be telling you the whole story. One example is you have a trace file, but you don't know where it came from. So who produced that trace file? Where do they capture it from? Does it make a difference if you capture packets near the client versus near the server? Does it make a difference? Yeah, it does, right? Because if I'm capturing near the server, my packet trace shows a packet going out. I don't know whether the client received that packet or not. So John was saying in his previous talk, very useful to have packet trace from both ends. Right, you want to have a packet trace near the client and one near the server, and you can see what's coming in and out of both ends of the conversation. But when you do that, you need to make sure you know which one is which. If you're merging those into one PCAP file, you might get confused about which packet was captured at which end of the connection. There's a few other problems you might have. One of them is, what if there was packet loss? Now, I don't mean packet loss on the network link, but I mean packet loss during the capture. So I'm looking at a PCAP file, it shows some packets seem to be missing. They were actually on the network link, but the capture system failed, didn't record those packets for some reason. Maybe it ran out of memory, maybe the disk wasn't fast enough or something like that. So you really need to know, when you're trying to analyze a file, was there any packet loss or not? Because if there might have been, your interpretation of that file might be wrong. Another case is, well, what if the packet trace, when it was captured, was done under a filter? So if anyone was in Hansang's talk this morning, he went through a packet trace where he had to spend a lot of time analyzing IPID sequence numbers in order to infer that there are packets missing from his trace file. So he thought that this trace file had everything that came in and out of that client machine, but actually there was a filter that was applied during capture, and he didn't know what it was. It turned out that there was a packet filter that was running that was filtering out all the ARP traffic. And because that was filtered out, he then had to try and figure out what was happening in the link. And finally, you don't know if the timestamps are right. So I give you a PCAP file, it's got a bunch of timestamps in it. How do you know what time zone they're in? How do you know whether the clock was actually accurate or not? So there's quite a few things you need to know about the PCAP file when somebody gives it to you beyond just the contents of the file. So what I'm going to talk about today, what is metadata? Why do we need it? What kinds of metadata are there that might be relevant to packet trace capture? And how can we use it in Wireshark? How can we encode it? How do you put it into a file? How do you read it back? How do you analyze it? There's a couple of different ways of doing that in Wireshark today. You can use PCAP-NG, which has been discussed a little bit today, and ERF. So ERF is the file format that Endace produces. It's called the Extensible Record Format. And as far as I know, those are the two file formats supported by Wireshark that have a significant amount of metadata available in them. And we'll talk a little bit about what's different about them, whether it makes a difference. So why do you need context? We've talked about a few of them already, potential problems. Scalable capture. First of all, if you're just recording on your laptop, you've probably got one interface. You know that that file on your laptop came from your laptop. Hopefully you remember where you took it and so on. But if you're in a large organization with lots of data centers, you may have packet capture systems distributed through your network. You might be doing packet captures on remote servers or in the cloud, and you need to know when you're looking at a particular file which you may have downloaded to your machine, where did it come from? Data mining, having context is very important. It allows you to search and index on all the different fields. Capture quality, we talked a little bit about that. You need to know whether, when you were capturing that data, was there any packet loss? Were the clocks synchronized properly? Legal evidence, can you say in a court of law, can you stand up and say, I know where this PCAP file came from, and I know that there was no loss in it? Timing accuracy, so what we're starting to see in Europe, there's some new regulations called MiFID II, where the regulators are requiring stock exchanges and traders to record everything that they do. Every packet that comes in and out, they have to timestamp it and record it and keep it for a certain period of time, and they have to demonstrate that their timestamps are accurate. It has to be within 100 microseconds of UTC. And the reason for that is when there's a flash crash in the stock market, the regulators want to be able to go back, collect packet traces from everybody, and then understand what happened in what order. And the order in which you find out pieces of information can have legal implications. Right? So if you're shorting trades and things like that. It can also be useful for event correlation. So if I've got a number of devices on my network, I've got my IDS and my firewall, and I've got a server and a client. If I want to compare events across all those devices, the clocks have to be synchronized, or else trying to compare things based on time is going to be much more difficult. And finally, quality of service monitoring. So if I want to monitor delays through the network between 2 points, again, the clocks have to be synchronized, or else you can't measure a delay accurately. Big data. So people like to talk about data lakes. They're going to collect all of this information. They're going to put it into a huge data repository, and they're going to do some machine learning, and they're going to do some cool stuff on that. But it's garbage in, garbage out, if you've heard of that before. So if the quality of the data going into the data lake is not good, if you don't understand where it came from or what the quality is, then the results you get out will be garbage as well. And finally, event annotation. So we can use metadata for things like automating our analysis and marking packets of interest within trace files. Okay, so what do we mean by metadata? I think most of us kind of have an instinctual understanding of what metadata means these days. This is a picture from SharkFest 16 in Europe, in the sunny Netherlands. It was quite a cold day, nothing like here. And so as well as the image, you can see, hopefully on the right-hand side, it's a little bit hard to see on the screen, some metadata. So the image file contains all of this stuff. And what the kinds of things that are in there are the time that the image was taken. And that's not the file timestamp. That's not when I copied the file from my phone to my PC. It's when the image was actually recorded. There's some stuff in there like the size of the image, the type of device that it was captured on, the shutter speed, whether or not the flash fired, and interestingly also the location. So the little map there is not stored in the image file, obviously, it's just the GPS location, but that metadata in the file allows the file viewer to then give a name for the location and to render a map, which again allows you to then search based on location. I want to find all the pictures that I took in Arnhem. It's much easier to do that than looking through the pictures individually. Just as a side note, if you open a JPEG image in Wireshark, it will dissect it and you can actually get the EXIF tags, but the display of them is not very friendly. So I don't just show that here because it's a little bit awkward. You have to know some of the mappings and stuff. But you can try it if you're interested. Wireshark can open all kinds of files. It's worth having a go. Okay, so what sort of types of metadata are there? Well, when you think about a photo, it's a point in time. It's a single thing, and there's no change. So you can capture all of the information you need about that point in time, and that's it. But if you think about shooting a video, then it's not just one frame, it's over time. So I can't record one location, because I might be moving the camera. So I need to record the location multiple times through that. It's dynamic metadata. So when I talk about static metadata for packet captures, I'm talking about things that don't change during the whole capture time. So what machine was doing the capture, which interfaces was I using, what were the software versions of the tools, and that kind of thing. Then for dynamic metadata, that's things that might change during the length of the capture. And this might not be 5 minutes, this might be a couple of hours, this might be a few days or weeks even. And during that time, your links might go up or down. So the interfaces you're looking at might change. DHCP might time out, you might get a different IP address on the interface. Your clock, which might be synchronized at the beginning of the capture, might lose its connection to its synchronization server. So the synchronization may actually get better or worse. And then there's post-capture annotations. So when you think about metadata for a photo, you're really only interested in what happened at the time. Later on, you might want to go back and add a comment to that photo. Some photo editors will let you do that. Same thing is true for trace files. So you think about trace files, some of the kinds of things you might add after you've captured the packets are things like user comments. This is kind of a killer app for metadata in Wireshark. Most requested feature in Wireshark, up until they did it, was the ability to put comments onto packets. And there's also other kinds of events and alerts you could add to packets automatically. Also flow records, application detection from DPI engines. You might have some AI machine learning tools which are inferring things about the data. You might be mapping the connections to users or connections to processes on servers, that kind of thing. So here's kind of a coverage map. This is not everything that you could possibly look for, but here are some kind of examples of the kinds of metadata that might be useful when you're looking at a trace file later on. So kind of imagine that you're going out to do a packet capture. 6 months later, you're going to reopen that file on your laptop. What do you need to know about the file? So obviously you need the packet contents. That's the main purpose of the packet trace. But you also want to know things like, when I captured that file, was there a filter that was being used? The timestamps tell us when the packets arrived at the capture point, but we also want to know, was the clock synchronized? If it was synchronized, what was it synchronized to? What was the upstream source for that? Which particular machine was it that did the packet capture? A simple PCAP file doesn't tell you where the capture was actually done. Why did you do the packet capture? So was it related to a customer query? Was there a ticket number in your system about that? Was it related to an IDS alert? Was it automatically done or was it manually done? You may want to know who authorized it. So if it's lawful intercept, you may need a warrant. If it's within a corporation, you might need sign-off from management in order to do a particular capture on a certain interface. And then how was the capture done? So what equipment did you use, what machine was it, what application did you use, was it that version of the application that has a bug in it that means it drops lots of packets, or was it the good version, which means that it works correctly, and what was happening with the link, so what speed was the interface. If I see a burst of packets to 800 megabits, is that a problem? It depends. Is it a 1 gigabit interface, or is it a 10 gigabit interface, or a 100 gigabit interface? So again, without the context, you can't really interpret whether that spike is a problem or not. Okay, so we've got some idea of what is metadata, what might be useful to capture, how can we actually do it today. There's kind of two main ways of doing it. Before we get into that, let's think a little bit about bad old days. So historically, packet capture is done in PCAP format. So just a quick question, who does their packet captures in PCAP? Hands up. Anybody doing packets in PCAP format? Yeah, a few people, 2 or 3. So PCAP's been around since, what, early 90s at least, if not earlier. Right now. It's a long time anyway. And it was intended really for ad hoc captures on a single interface for a fairly short amount of time. The idea was memory is expensive, disk is expensive, you're probably not going to capture a lot of packets, you probably will capture it under a filter. So when you look at the PCAP file format, there's not very much in it. There's a fixed header which has got version information in it. It does tell you what time zone you're in. The timestamps are assumed to be in UTC, I think. There is a timestamp accuracy field, but it turns out that the PCAP doesn't either read it or write it. So as far as I know, it's never been used by anybody. There's a capture length and there's a link time. So I know, was this an Ethernet connection? Was it a dial-up modem? Was it PPPoE? That kind of thing.
Are you sure about the time zone?
There is a what they call time offset field. I think it's in seconds.
Okay.
Yeah, it's a signed field in the PCAP header. Again, it's not clear that anyone ever used it, but it is in there. It's defined.
I should use it.
Yeah. I think last time I talked to Guy, he was like, yeah, let's not go there.
Okay.
But have a look if you're interested. And then what you have is, after the file header, you get a sequence of packet records. Now each packet record has got a timestamp on it, so you know when the packet arrived. You've got the captured length, so how many bytes from the individual packet did I get, and how long was the packet when it was actually on the wire. So the PCAP has the idea that you can capture less than the whole packet if you want, or just capture the first 200 bytes of every frame. And then of course you get the contents of the packet. I would open one to show you, but my laptop's not cooperating, so I should give you a screenshot, which you probably can't see very well. It's a bit hopeless. Wow, that's really bad, isn't it? What I was going to show you is that when you look in here, if you can open files yourself, there's no interface ID, right? So when you open a PCAP file, there is only one interface. It doesn't tell you any information about where that's coming from. Here we go. That's slightly better. Okay, so there you go. So we can look at the top of the frame dissector in Wireshark. Will, if there is interface information, will list it right near the top, and there's nothing there. Okay. And where do you look for metadata in Wireshark? You open the, you go to the statistics menu and you open capture file properties, and it'll give you some indication of what's there. If you have a look through it, you can see that there's a whole bunch of fields marked unknown, 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 unknown. That's because PCAP doesn't record any of that information. It's just not there. It's not in the file. And also, PCAP doesn't support packet comments, and it doesn't support file comments either. So if you try and add comments to it and save it, you won't save it in PCAP format, or if you do, you'll lose them. You'll have to save it in PCAP-NG instead. So people realized that this was a problem. And when we look at our coverage map of the kind of stuff that we want to capture, PCAP doesn't get very much of it. It gives us the contents of the packet, a timestamp, maybe it gives us the timestamp resolution if you're being generous, maybe it gives us the time zone offset, it's not quite clear, that's about it. Everything else that you need to record, you have to write down in your notebook, when you're doing a capture, or you have to encode it into file name. So when you look at PCAP files, you often see this complicated directory structure and these very long file names, where people are writing 20 different pieces of information into the file name, because that's the only place you can store that information. So people realized a long time ago that this wasn't a great way of doing packet capture, and we want to capture more information about what we're doing. So they came up with PCAP-NG. PCAP-NG is a block-based kind of file format with options. So when you can add options, suddenly you've got a lot more possibilities. So PCAP-NG has currently got at least 30 tags, somewhere north of 30 different pieces of information you can store. And very importantly, it natively supports multiple interfaces. So if I have a PCAP-NG file, I can capture from more than one network interface and record for each frame which interface it came from. And it's extendable. So it's very easy for people to add more tags. It is a standardized process, but you can get vendor tags. Individual vendors can get their own namespace and add their own tags. It's been around for quite a while. There's been a couple of IETF drafts, 2004, 2014. None of them have made them to RFC or standards basis, but there is documentation out there. And if you're looking for it, it's on GitHub. So on GitHub, PCAP-NG is actually the standard. It's not an implementation of PCAP-NG. This is the standards document itself is in GitHub, so you can go and have a look at it. It's been supported in Wireshark since 2009, which is quite a while after it was originally invented. It's been readable by libpcap since 1.1 version of libpcap. So if you have a PCAP-NG file and you have an application that uses libpcap, that application can read the PCAP-NG file, but it will lose all of the metadata. It will only read it as if it was a PCAP file. So for backwards compatibility, it's okay, but it doesn't really help. And then finally, it's been PCAP-NG as the default save format in Wireshark since 2012. So if you're doing your captures using Wireshark or T-Shark, the command line version, you're probably getting PCAP-NG files already. So what's in a PCAP-NG file? A number of different block types. We start off with a section header block. In this slide, the things which are bold are mandatory, and the things that are in italics are options. So depending on your implementation, they might be in there or they might not. Even different platforms sometimes support different sets of fields. So the section header block is kind of information about the entire capture. Things like what was the hardware that was used, what was the OS, what was the application versions. And then you get interface description blocks, one for each interface, where you have link types. So it's possible to do a simultaneous capture on a wired Ethernet network and a Wi-Fi interface at the same time. They can have different link types within the same file. You can also record things like the addresses of the interface, the name of the interface, timestamp resolution independently per interface. If there was a capture filter, that's optionally in there. So it doesn't mean that if it's not listed that there wasn't one, but if there is a filter, there is an option to save it. Then the packets themselves are stored in what's called the enhanced packet block. There used to be a packet block and a simple packet block, but they've been removed from the standard, so there's only the enhanced packet block. And the packet block has got which interface the frame was captured on, what the timestamp was, the lengths, and the contents of the packet. And there's a few options you can have there, like error flags and indications of packet drop. And then finally, actually there's a couple more. There's a name resolution block, which allows you to record into the trace file mappings between names and IPs, names and addresses, IPv4 and IPv6. Last couple, so there's an interface statistics block, which can be stored in the file that records information about a specific interface, and it can have things like packet counts, packet drops, and so on. Lastly, there is a number of experimental blocks that have been proposed for storing information about things like compression and encryption, different types of indexes, so you can search through a file quickly, statistics, events, and vendor extensions. None of those are necessarily implemented, but they've been proposed as, hey, this might be a good idea. So what does it look like? You can kind of imagine a PCAP file as being a sequence of records or blocks. You always start with a single section header block. You get one interface description block for each of the interfaces that's used in the capture file, and the standard says that the IDB has to occur before any packets that use that interface. So you can't have a packet and then the interface that describes it. And at the end of the file you get some name resolution blocks. I think in Wireshark they're a maximum of 2 megabytes each, so you just get as many as you need in order to store all the resolved names in the file. And then you get one interface statistics block per interface. So at the very end of the file, Wireshark adds up the number of packets and writes out some statistics. Now the file format itself does support more than that. You can have things out of order and have multiple sections and all this kind of stuff, but Wireshark doesn't support those. This is basically what Wireshark supports. Just as a note, one thing that always confused me is the Wireshark user manual says resolved names are not stored in the file, but they are stored in the file if you're using PCAP-NG. So I think that's maybe something that's obsolete. There was also a bug in Wireshark 2.2 that meant that they weren't stored in the file, even if you were using PCAP-NG. That was then fixed, so they are now stored in the file again. So if you're not sure, you have to have a look. Okay, so if we open a PCAP-NG file in Wireshark, which you might be able to see, zoom in a little bit. What you can see just under the frame at the top, interface ID, device NPF, some horrible number. So that is the name of the interface that this packet was captured on in Windows. So Windows gives each of their interfaces a globally unique ID string. So in theory, if I had a map for all of those GUIDs, I could know which particular machine, which interface it was that packet was captured on. And every packet that's in the trace file will have an interface ID number. That number is assigned by Wireshark. You also notice when you're looking at this file, if we zoom up a little bit, what we see is packets. Right? So look at the first item in the packet list, it's a packet. I don't see the section header block or the interface description blocks. They don't show up in here at all. What you can do, and I can't show you because I don't have the live demo working, is if you go to View menu, you can switch to File View mode in Wireshark. It's down the bottom of that menu. And what will happen is instead of looking at the packet pane with all the packets in it, you'll see all the blocks in it instead. So the first block will be the section header block. You'll see the interface description blocks, and you can open those up in tree style, and you can look at the contents of all the metadata that's there. As a note, when you're in Linux doesn't use globally unique ID for the interface name. Instead, it'll just call it ETH0. So, for example, ETH0 means something more to a human, but it's not globally unique. So there's kind of either or, and you can kind of tell from the interface names what kind of machine the file was captured on. Okay, so if we do go to the capture file properties and have a look, what we can now see is a PCAP-NG file. There's a lot more fields filled in. So if you look under capture hardware is unknown. That's because we're in Windows. The Windows version of Wireshark doesn't write anything into the hardware field, but it does fill in the OS, 64-bit Windows 10, and the application dumpcap, which is part of the Wireshark tool. And this is 227. It also, when we look in the interface section, we get the names of the interfaces that we used in this capture file. Again, you can't really tell what they are, but they were two different interfaces. I think one was Wi-Fi and one was Ethernet. It also gives us drop packet counts. That's something that comes through in the PCAP-NG file. And it also tells us capture filters. So if Hansung this morning had a PCAP-NG file instead of a PCAP file, and he thought maybe there's a filter applied, he could have just gone to capture file dialog properties, and you would have been able to see that there was a filter there filtering out ARP. Finally, if we scroll down a little bit, there's capture file comments. So there's a comment on this file that says add name resolution. Okay. Oh yeah, scroll down a little bit more so you can see the bottom part. The drop packet counts come from the PCAP. So when the capture is in progress, the capture library keeps track of how many packets have dropped, and it stores them on a per interface basis. And the packet sets, these packet sets down here in the statistics section are not actually inside the trace file. These are things that Wireshark calculated as it was reading the file in. Okay. Okay, so here's an example of a packet comment. Zoom in a little bit. So here's a packet and it has a comment on it. I like this one. It's a good comment. The way that PCAP-NG stores comments is it puts them as a comment field inside the enhanced packet block. So if you have a trace file open and you start adding some comments, the comments are not stored until you save the file. So keep that in mind. And if you go to close Wireshark, it'll say, oh, do you want to save that? And you think, well, what's changed? Well, what changed is you added some comments. And when you do that, it'll rewrite the entire file out again, and in that one packet block, it will add the comment string. So if you think about a coverage map, what kind of stuff does PCAP-NG gives us? It gives us a lot more, right, than what we saw with PCAP. We're now getting a lot more information. We're getting the capture filter. We're getting information about the timestamp resolution, the link name, the interface ID. We're supporting multiple interfaces. We're getting information about how we captured the file, the hardware model, and so on. And most importantly, we get the ability to add comments. And you think about it, the ability to add comments means we can use that as a get out of jail card. So anything else here that we want to record, we can just put it in a comment. Right? The only problem is you have to remember to do that manually. If you're not actually going in and editing the capture file comments and putting all that stuff in, then you won't have it 6 months down the track when you're trying to understand what this file is about. Another thing that we don't have is display filter. So one thing you can do in Wireshark is you can use a display filter to select some of the packets. You can do a save as, and you can save only the packets that match the filter. So you've now created a new file that has less packets in it.
Don't use save as, use export packet bytes.
Sorry, export packet bytes, you're correct. And you can choose the format, so you can choose PCAP-NG. And what will happen is it will still record the capture filter that was used, which is the BPF filter, but it doesn't record the display filter, unfortunately. I was just talking to the core developers about that the other day, and hopefully that's something we could get in future. I think it'd be kind of nice.
Put it manually in the...
At the moment you'd have to cut and paste, so you could copy the display filter dialog and then paste it into the packet comments or the file comments. But if you forget to do it, then you won't know. It's very confusing when you open the file later. You can see the capture filter, and it says, oh yeah, there was no ARP. When you look in the file, there's no DNS. But the filter says something else. But you've actually filtered more stuff out since you did that filter. So you've changed the filter. Okay. So at Endas we looked at that and we thought that was pretty good. Our own devices produce a different file format, which is older than PCAP-NG in fact. So the ERF format is what comes out of our hardware and comes out of our appliances. We don't produce PCAP-NG natively. And the way that it works is it's just a stream of records. So we don't have a file header, it's not really a file format, it's just a sequence of records. We've had ERF support in Wireshark since it was not called Wireshark, since it was called Ethereal, 0915, and back in 2003. And I had to go and look that up in the subversion logs to try and find out which version it was. And we have full support in modern Wireshark, so Wireshark 2. Whatever, we're completely up to date. It's actively developed. You can do live capture in Wireshark using the PCAP. And we dissect all of the ERF record fields, including expert info and so on. And then metadata support we've added relatively recently. So since Wireshark 2.2, you can now encode Wireshark format metadata can be stored in ERF, and ERF native metadata can be displayed in Wireshark. And as of Wireshark 2.4, we support file comments. So we support capture file comments and per packet comments. So when you save a trace file that you've added comments to, you can also do it in ERF rather than just in PCAP-NG. Why did we do it? Our hardware produces a different format, and we also wanted to see how can we extend it. So Wireshark's doing a good job. What is some more metadata that we could put in? So what we did is we came up with a new record type for storing metadata. What's interesting about it is that it has a naming scheme which is rather than just the name of one interface, we store the name of the capture system, so what was the actual machine that did the capture, which interface, which card within the capture system did the capture, and which interface within that. The time that the metadata is generated is recorded. We have multiple sections. There's over 160 different items of information you can store, up to 64K per record, and we have an append on update policy. And what I mean is, if you want to change a comment, rather than editing the contents of it, we add a new record with a changed version. So that way you always have an auditable history of what comments were made over time, even if they were deleted. And this is kind of what it looks like. So rather than being a file format, we have a file header and then contents and then the end. ERF is really more of a infinite stream of records, if you like. And what we do there is we just drop provenance records in periodically. Typically that's once every second. One of the advantages of that is if I have days worth of captured data and I want to extract only a short period from the middle of it, I know that when I capture just a small part of it, I'll get the metadata that's relevant to that particular period of time. So what sort of stuff is in there? This is not all 160 tags because that would take a long time. This is kind of an overview. So there's a few different sections. Capture section is about the entire capture. So name and description, who was the user who did it, what was the time zone they were in. There's information about the capture system, so the host, OS versions, tools, all that kind of stuff. There's information what we're calling the module section here, is the capture device. What was the firmware version, all that sort of thing. Clock synchronization state. There's sections about each of the interfaces within the capture card, so what was the interface type and link speed and so on. And finally the stream. So within our devices there are multiple queues, if you like. Each one of those is where the loss occurs. So if there's packet drop, it occurs on a stream basis. So if you open one of these up in Wireshark, then what we see is something quite similar to PCAP-NG. One of the differences is, if you look at the white line through the middle, you can actually see the provenance record. It shows up in the packet list. So with PCAP-NG, if you want to see the metadata, you have to switch to file view. In the ERF, we decided just to make it show up in the packet list. So once per second, you can see the timestamp 44.0000. That'll be where you look for that metadata. If you look at one of the packet records, so packet 1.
Is that a separate link layer type then, or is it? Or is it a special type within the ERF format? It's
a special ERF format type, that's right. So when you look at a regular packet record like packet 1, the ERF type is actually down here, but it'll be an Ethernet frame, so I'll have an Ethernet type. The provenance record has a metadata type instead. And you can see here in the interface name we've got this kind of long string. So interface ID 0 is the number that Wireshark's assigned. Then you've got port A, and port A was the name of the interface that the user gave to that interface. So port A is just a default. And then inside the brackets you've got a hierarchical name. So you've got a host ID, which is a GUID, which card within the machine, so that's the source, and then which interface within the card was that packet captured on. If you decide that you don't like to see those white records every second because it's confusing you or just distracting, you can just filter it out. You can just go into the record type and say, okay, don't show me those provenance records, and they'll just disappear. Okay, if you have a look at the file capture dialog again, so this time we see that it's an index ERF capture, extensible record format, and we see that we've got the hardware type field is filled in, the OS is filled in, and the application type is filled in. So that was the application that generated the metadata. And we can see that this capture was done in Linux, which has a bit more information in it, including the name of the machine. And then each of the interfaces that was used for the capture shows up down here. Packet drops, capture filter, capture length, and so on. The reason that there's no packet drop shown there is that the drop occurs on a stream basis, not on a physical interface basis. So it shows up elsewhere. It is still tracked, it's just not listed there. So because these provenance records, we'll click on one of them and have a quick look. Because these provenance records show up in the packet list, they're all dissected. So every element that's within there is a Wireshark dissector field, and you can filter on it, you can search for it, you can display it, you can put it into I/O graphs if you want, all that kind of stuff. If you look right down the very bottom right-hand section of the screen, you can see the field that's selected shows up as Earth Meta Section Module Clock Port Protocol. Okay, so those things are all registered in the usual way. And you can see those for PCAP-NG, you just have to switch to file view first, and then they're all dissected as well. Okay, so you can open up some of these sections and have a quick look. So here's some of the information that's in the capture section. We've got the name of the capture, which is example capture, the description. These are fields which are filled in manually, right? So at some point you still have to go and configure what those strings are. Most of the rest of the metadata is collected automatically. So the application name, the time zone offset, time zone name, all of those things are filled in by the capture application automatically. The host section has got all the information about the machine. So this was a machine that was in my test lab back in New Zealand. You can see the name of the machine, you can see the type of CPUs it had, what OS it was running, what version of the DAG software was installed, all that kind of stuff. There's a lot more information there than you would get from, say, just a CPU ID string. Okay, so if you look at our coverage map, I won't go through all of the fields there because there's a lot of them. You can download example ERF files with provenance from the Wireshark pages. We cover a lot more stuff. We don't get quite everything, I don't think. We still don't have display filters. There's no way to get hold of that information in Wireshark at the moment. MTB, what I'm talking about here is packet brokers. So if you go to one of these vendors like Gigamon or Exia, they have an external packet aggregator which might be doing load balancing or filtering. At the moment, the information about what that device is doing is not stored in the file. Right? We don't have a way of getting that. And we would have to work with each of those vendors individually because there's no standard for how you would access that information. So that would be useful stuff to get. But generally, I think we've got quite a lot of stuff. All of the Earth and metadata fields that have been defined are dissected by Wireshark, even if we haven't implemented them at capture time. So it is pretty complete. And if you want to convert between PCAP-NG and Earth and backwards, we do as much as we can in terms of copying all the fields over. Some of them don't translate very well, but most of them work pretty well. How do comments work? It's kind of worth touching on very briefly since it's an important use of metadata in Wireshark. PCAP-NG has the ability to put a comment on any type of block. It's an option that's allowable anywhere. So the way Wireshark does it is if you have a capture file comment, it goes on the section header block, and if you have a packet comment, it goes on the packet block. It turns out that the name resolution block and the interface statistics blocks also have comments on them which say something like, this data was provided by dumpcap, and that's it. You won't see those comments unless you actually open it in file view. Earth, the way that we add a comment is we add an entire new provenance record. So if I have a packet and I want to add a comment to it, I insert an entirely new provenance record. And that provenance record could have any type of tag in it that you want. So what we do at the moment is we have a comment string tag that we put in that has the context of the text that you've typed in, but we also record the timestamp for when you added the comment. We record the host ID as the machine that you added the comment on. So if I record a trace file on some server, then I download the trace file to my laptop and then add a comment, I'll get the ID of the laptop will get put into it, and also the username. So Wireshark can actually get the username of the current user who's running, and it'll put that in as well. And when you're looking for those, so if you then save that comment in Wireshark and then open the file again, you'll discover there's one extra record in the list. So as well as the Wireshark comment showing up as normal, as it would on the packet, you can actually also see the extra dissection information. You can see the timestamp and so on. And the capture file we store in the capture section. So kind of a summary, if you like. PCAP-NG is very much a file-based approach. There's one set of metadata that's static that covers the whole trace file. It works very well as long as the metadata doesn't change. So if it's for a fairly short time period, it works fine. If it was a longer time period, you'd probably want to break it up into multiple sections. But Wireshark currently doesn't support that, as far as I know. It's pretty lightweight because there's only one record at the beginning. It does support multiple interfaces. Where ERF is different is that we drop metadata in every second into the file. So it makes it fairly easy to seek to the middle of multiple days of data, extract a short piece of period of time, and get the metadata that's relative just to that piece of data. It's scalable, so we support multiple hosts and interfaces.
So what kind of data would be dynamic? So I can see some of the use cases for the provenance record, but the majority of what I've seen is relatively static.
Yeah, sure.
So in that use case, over 2 days, you've got a couple of terabytes of data.
Absolutely.
What kind of dynamic auto-generated metadata would those provenance records include?
So you're right, a lot of the metadata is static, right? So the name of the machine that's doing the capture is probably not going to change during that time. So every second you're writing the name of the machine that's doing the capture into a file, which might seem a little bit redundant. The kind of stuff that does change over time is clock synchronization is quite important. So I didn't actually show a demonstration of it here, but we capture, if you're using precision time protocol, we record a lot of PTP state. So we record the offset from master, which master clock are you using, what are the error estimates, what are the round trip times, and so on. So there's a whole bunch of stuff in there, including the flags that indicate whether the time standard is traceable to UTC or not. So for financial guys, that's quite useful. Also, if you have a capture session that runs long enough, you're going to see interfaces going up and down. You may even see link speed changing. So if you've seen energy efficient Ethernet, this is Ethernet which changes rate between, say, 100 megabit, gigabit, and 10 gigabit, depending on how much traffic is going over it. So in order to save power, it actually slows down. And knowing when those transitions are would be quite useful potentially. So yeah, some of it is redundant, but again, it does mean that if I seek, if I've got terabytes of data, I can clip out little bits from the middle, and I don't have to try and go back and find the information from the beginning of the file, because it's always going to be there. Another thing that can be done is you can distribute the name resolution blocks at the end of each second. So at the end of every second, I have a name resolution set of records, which have the name lookups for what was during that 1 second. Whereas at the moment, at least, in Wireshark, it puts all of the name resolution blocks at the far end. So if you want to clip out the middle, you kind of have to read the whole file. That makes sense. Good question. And it's very scalable. So the fact that we support multiple hosts as well as multiple interfaces means you can do, for example, if I've got a lot of capture probes, I can do a query and say I want to find this IP address on 100 different capture machines, get a single file back, and I can tell for each file within that, for each packet within the file, which particular capture machine that it came from. So it's well designed for continuous capture where the environment is dynamic. Things are changing over time. So conclusions, don't take this as a beat up on PCAP-NG. PCAP-NG is a good file format. It works very well, and it's extendable. So there's nothing that's being recorded in ERF today that couldn't also be stored in PCAP-NG. It's just a matter of someone defining the fields and then writing a capture application that collects that information and populates it into the formats. So dump cap in Wireshark captures as much as it can, but it doesn't get some of that detail. So trace metadata is really important. You can't interpret a trace file unless you know the context that it was captured in. That's probably the main takeaway. The quality of packet captures does matter. You can't just assume because somebody gives you a trace file that it's complete or that it's very accurate. There are different types of metadata, so we've sort of talked about that a little bit. The information that's static, but also the information that's dynamic, and the information that was added later. And if I'm adding information to a trace file later, I want to be really clear about what was added, who added it, and when did they add it. Otherwise, it's just someone modifying the information that was in that trace file. Metadata is great. Automatic metadata is best because you don't have to do it yourself. If you leave it up to the user to have to type in descriptions of what they're doing and why they're doing it and enter the ticket number manually, they'll forget or they'll get lazy. And then 2 years later you open the file and you have no idea what it's about. And the good news is all of this stuff is already in Wireshark. So if you have Wireshark, you can be capturing in PCAP-NG. You can collect a lot of this metadata automatically. Encourage other people to use PCAP-NG in Wireshark. And when you're sharing files, so whether it's in class, whether it's sending emails, a trace file to a colleague, try using a format that supports metadata. Sometimes you have to use PCAP because it's the only format that the tool will read. It's very easy to down convert. I can take PCAP-NG and I can convert it to a PCAP file very easily. If I only have a PCAP file, I can't get the metadata back. It's one way. All right. Thanks very much. Any questions?
The packet comments, where are these saved in ERF?
So in ERF, what we do is we insert an entire new record.
Okay.
So you would go to where the packet is, packet number 500. We would insert a new record immediately before 500 that has the comment in it. And in the extension headers, it would say, this comment refers to packet 500. So it'd be a little pointer saying which packet it is.
Are there absolute packet numbers in the ERF format?
What it does, it's a little bit more complicated. What it actually does is it generates an ID, which it sticks into the packet you're adding the comment to in the header, and then it uses that ID number inside the comment record, so there's a direct tie.
This ERF format, is that open source or is it public? Or?
It's publicly defined, so you can download the format for it, and Wireshark is a complete dissection of it, so everything that's available is in there.
Okay, so it's an open format.
It is an open format, so other people do generate it.
Yeah.
If you've seen a very modern Intel server, they have a fabric on it called OmniPath, which is a 100 gigabit CPU to CPU fabric. And when Intel wanted to come up with a capture format for that, they actually used ERF rather than PCAP-NG because there was a mapping for it, basically. And there's support for that in Wireshark. So if you're doing OmniPath captures, open them in Wireshark, you'll see the ERF layer inside there.
Stephen, can you explain a bit more on the network packet brokers thing?
Packet brokers. Yeah, sure. So when you think about packet capture, sometimes you're just capturing on the endpoint, right? So if I'm doing a packet capture on here, I'm seeing all the packets coming to and from this machine from some servers. But if I'm, there's a lot of disadvantages to doing that, right? So we get offloads and things like that. So you're not necessarily seeing the packets on the wire. So you can put in a tap. A simple tap will just tap the cable and it'll give you a copy of all the packets going past in each direction. And there's really no problem with that because you're only looking at one link. Packet aggregator is a box, usually like a rack mount box. It'll have 20 or 30 ports on it. And internally, that packet aggregator modifies your traffic. It might add a timestamp to the end of the packet or the beginning of the packet. It can take packets from multiple ports and merge them together. It can also filter things or load balance. So when you put Wireshark on the end of that and just capture that into one file, It's only one interface as far as Wireshark is concerned. It can't distinguish between them. Sometimes there's a trailer which says which interface it is. But you really like to know some information about what was the upstream port that was connected to, which link was it on, what speed was that link.
So you get from Gigamon
Yeah. So what we'd like to do is to say, let's have an API where we talk to Gigamon, collect the configuration information about that, store that in the file as well. Yeah. And there's a bunch of different vendors. Gigamon's one, Axia, there's quite a few.
So it's basically accountability, right? More detailed.
It's about accountability, that's right, and providing an audit history. So if you have to say to your boss, yeah, you know, this is where the problem is, you can actually back it up. And you can say, here's the evidence, this is where it came from. And something I alluded to is, most of us have a directory on our laptop with 50 capture files in it, and they're called, you know, New York.pcap or something. And 6 months later, you have no idea where you captured it or why you did it, what's wrong with it. When you look at the Laura's packet lab, all of her capture files are in PCAP-NG, and she has comments on the individual packets about, well, this packet, you know, has a bad, you know, checksum or something like that, so that you can go back and search for them later.
Do you any signing with certificates? Like you can say, okay, this certificate or this person with this certificate actually made this trace file, this host or this device with this certificate made the trace file.
It's an interesting idea, yeah, the idea of actually signing the trace file with a checksum over it so that it can't be modified without changing it. I have thought about that, we haven't implemented that yet, but it's something you could easily do. I think that you could probably do the same thing in PCAP-NG.
Yeah.
So if you generated a SHA
it's in my head for a while.
and then put a certificate in, yeah, absolutely. Yeah. Okay. I know I'm between you and dinner, so we'll wrap up there. Thank you very much.